let's talk about what we would do if this problem were an inequality. So if I have a greater than or equal to sign here, we saw the example of equals a minute ago. So I want to use this to highlight two things. First of all, I want to highlight a different approach to the fractions in this problem than we used in the example we just did. And we also have to highlight how solving an inequality is almost the same, but there's one different wrinkle to solving with an equal sign. So we still have the same set of priorities. We need to get all the x's onto one side of the equation and then get them by themselves by reversing the order of operations. But the first thing I want to do here, again, is to approach the fractions in this problem a little bit differently. And I'm going to do that by applying one step, one magic wand at the beginning of this problem that's going to get rid of all of our fractions for us. Which is great, because that means that we're going to have to do all of our fraction thinking front-loaded. Do it right now, and then the rest of my problem is only going to have whole numbers, which is always good when you can get away with it. This is called the method of clearing denominators. And the idea behind it is that I want to multiply both sides of my inequality, in this example, but we can also use this with equations. Multiply both sides by, in this example, we only have one fraction, so this is going to be a little bit simpler than some of the others. But if I had multiple fractions, what I would just do is I would find any common denominator. For all the fractional coefficients. So in this example, we only have one denominator to work with, 3. So we can just use 3 as the number that we're going to multiply both sides of this inequality by. And the benefit of doing that is now when I apply the distributive property, that 3 is going to multiply every one of the 4 terms in my inequality. And for those terms that were already whole numbers, they're still going to be whole numbers after we multiply, right? -1 is going to become -3. X is going to turn into 3x. 4 is going to turn into 12. Here's my inequality symbol. But the real magic happens right here. When I multiply 3 by 2/3, let's look at that multiplication problem in isolation here for a second. 3 times 2/3. Again, 3 we can think of as 3 over 1. And we can then multiply straight across, if we wanted to. And if I do multiply straight across, I'm going to get 6 on top and 3 on the bottom. But what's 6 over 3 better known as? It's better known as 2. The whole number 2. And so what I end up with here is 2x. And all my fractions are gone. That's the beauty of this method, is we front load thinking about fractions, and we use it to just wipe out all of our fractions in one fell swoop. Now we're back to an inequality or an equation, depending on the problem, where we only have whole number coefficients. And what could be better than that? So now we can go back to our strategy for getting all the variables to one side, which I'm going to do by subtracting 3x here. 2x minus 3x is going to give me -1x minus 3, greater than or equal to 12. Then, reversing the order of operations, I worry about multiplication and division only after I worry about addition and subtraction. So I do addition and subtraction first to move that 3 away from the x and give me -1 times x. I'm going to make that a little more explicit there, greater than or equal to 15. And then my last step to get the x by itself is to do what? Undo this multiplication by dividing. On my right-hand side, 15 divided by -1, -15. On my left-hand side, -1x divided by -1 is going to leave me with just x. But, here's my last question. What about this? What about the inequality symbol? So yeah, in this last step, our inequality symbol reverses. Why? What is it about the last step that we did that clues us in to the fact that the inequality needs to reverse at that step? It's in what we multiplied or divided by. So here we divided by -1. And anytime you multiply or divide an inequality by a negative number, the inequality symbol has to reverse. Because multiplying or dividing the number line by a negative number actually reverses the whole order of the number line. If I take everything on the number line, multiply it by -1, that whole number line flip-flops from right to left. And so our sense of order, our sense of direction flip-flops. Right? It's like taking a car that's driving north and just suddenly plopping it back down facing south. Right? Our whole sense of direction has changed. So anytime you multiply or divide an inequality by a negative quantity, that inequality needs to reverse. And so our answer then for this inequality is x is less than or equal to -15. So again, we use this to illustrate two different things. The first was that we can wipe out all of our fractions in an equation or an inequality by using this method of clearing denominators. I cannot speak highly enough of this, because anytime you can reduce your exposure to fraction arithmetic, you reduce your exposure to making fraction-related errors, and that helps everybody. So we did that by multiplying both sides by 3, which was a common denominator for all of our fractional coefficients. And then after that, we got all the x's to one side. We reversed the order of operations to get the x by itself. And then in the step where we divided by a negative number, we divided by -1 here, we reversed the inequality from greater than or equal to less than or equal to. My last comment about this is that another thing that bogs people down in working with inequalities is in how you express, how you report your answers. So there are two modes of expressing your answer in an inequality problem that are different from just reporting your answer as x less than or equal to -15. One of them, actually maybe there's 3. One of them is to write your answer as a set. This is something that the web work and Orca, our textbook, have us do. Set notation just takes and includes a set of curly braces around our answer, and then a little extra notation in the beginning. Because what this does is it makes it into a mathematical sentence. Our solution to this inequality is the set of all x's such that x is less than or equal to -15. So just a couple little extra elements of notation to make that into a complete sentence. The second way to do it is to answer with a graph on the number line. So if I'm thinking about the x's which are less than or equal to -15, on my real number line here, -15 is somewhere over here to the left of 0. And if I want to sketch that solution, what I would do is I would first note that which numbers on the number line do I want that are less than or equal to -15? Are those going to be the numbers to the left of -15 or to the right of -15? If we're thinking less than or equal to. Yeah, those would be the numbers to the left. So I'm going to start by shading all of the number line that lies to the left of -15. And then the next thing I'm going to do is answer, well, what about -15 itself? Is -15 itself included in my solution or not? Is it true that -15 is less than or equal to -15? It is true. And so to reinforce that, I'm going to also put a big closed circle right here at -15. So there's my sketch for what this solution looks like on the number line. And finally, we'll translate that sketch into one last different type of answer called interval notation. For interval notation, what I want to do is write out what is the lower limit and what is the upper limit of my solution. First of all, starting with my upper limit, how far up on the number line does this set go? -15. That becomes my upper limit. How far down on this number line does my solution go? Yeah, exactly. It never stops. So it goes all the way out to what we call -infinity. And then we'll add one extra piece of notation into this that tells us whether or not we include -15 and whether or not we include -infinity in our answer. Well, -infinity is not a number. Right? And so it is never included in any of our sets that are solutions of inequalities. And so to note that, we're going to put a little round bracket that means not included. I guess you'd call it a parenthesis. Not included. Where we don't write not included, we just write the parenthesis. But negative 15 we decided was included, and so we'll use a different notation for that. For that we'll use a square bracket. For is included. And so the interval notation for this answer would be negative infinity with a round bracket, comma, negative 15 with a square bracket.